Okay, in this video I'm going to be talking about kinetic molecular theory. I'm going to talk about, there's lots of evidence that came together to make up this theory or to give us the idea of this theory, but I'm just going to talk about two main experiments and with why those experiments lead to these types of conclusions. So the first experiment I'm going to talk about is the electrolysis of water. So let's say you have a container of water and you take two test tubes, you fill them with water, and you submerge them upside down inside the beaker of water. This should be distilled water for this to work properly. Then you take a battery. It's going to need to be a large battery, so we'll put lots of cells in here. And you put one end of the battery into one end of the water, and you put a second end of the battery into the other end of the test tube in the water. And what that does is the electricity will cause the decomposition of water into hydrogen gas and oxygen gas. Now, if we balance this chemical equation, what we can see is that as water decomposes, for every two hydrogen gas molecules that created, we only create one oxygen gas, which means if this test tube is the one, I did that backwards. This test tube is the one getting the hydrogen gas, and this test tube is the one getting the oxygen gas. Then the amount of oxygen gas that's produced, we should always produce twice as much hydrogen gas. Okay? Now the ratio here works out to be exactly 2 to 1, regardless of how long you do this experiment or anything else, any of the other factors. Now what we know now is that the reason for this is that the volume of a gas is directly proportional to the number of gas particles, assuming all other factors are being held constant. So, and assuming it's acting as an ideal gas. But if if we're always getting 2 to 1, the real conclusion here, or the idea here, is that there must be these finite building blocks that are reacting in a definite proportion for this to maintain such a stable ratio. Imagine, for example, instead of there being real hydrogen particles and real oxygen particles, that there was a continuous amount of hydrogen, a continuous amount of oxygen that was part of this substance. When you divided that up, you could, as on average, get a ratio of 2 to 1, but you could imagine that it would be very easy to get a ratio of 1.9 to 1 or 2.1 to 1. So the fact that it always comes back to this ratio right here means that there must be 2 particles of this for every 1 particle of this. With that in mind, that's at least one of the pieces of evidence that would have been used to come up with the first 2 tenets of particle theory. Number 1, all matter is made up of particles. See, it had to be in that discrete unit, and that's what leads to that fixed ratio. And number 2, different types of particles make up different types of matter. See, when you do that, for example, if you take the hydrogen gas and you expose it to fire, you'll get a little pop, and if you take the oxygen gas, you'll just get the flame growing bigger, but you won't get any sound or any little bit of an explosion. So obviously those different types of matters are made up of different types of particles with different properties. The second experiment comes from the idea of temperature and heat and what they used to think, and the sort of classic example of an experiment where that broke down. And that is that they used to think, imagine for example that you take a hot piece of metal, let's say you take this piece of metal and you heat it up to, let's say, 300 degrees Celsius. And then you take that metal and you put it in a beaker of water, and that water is like 20 degrees Celsius. And you can think about doing this, say, when you're heating up at a blacksmith shop, you're heating up a horseshoe, you heat it up so that you can change the shape of the metal, and then you put it in the water. What they used to think was that heat would flow from the hot object to the cold object. So heat itself, they thought, was a substance, and that's actually where the term calorie comes from, because they thought that there'd be calories of this substance. and that heat would flow from one substance to another substance. The classic experiment where this broke down is essentially with friction. Imagine a horse that was tied to a wheel that could be used to grind grain or something like that, and the horse is pulling the axle of the grinding mechanism around and around and around. And what they found was, when that happened, both the axle and the surrounding material both got hotter at the same time. So heat couldn't have been flowing from the axle to the material, or it couldn't have been flowing from the material to the axle, because they were both getting hotter at the same time. And a similar idea, if you just take your hands and you rub them together and you notice that both hands are getting warmer, where is that heat coming from? It's not like heat can flow from one of your hands to your other hand, and they both get hotter. If you had one hand that was hot and another hand that was cold, you could put them together and they would and then the heat would flow from one to the other, if you wanted to think of it that way. But when you rub them against each other, there seems to be some source of heat that's produced that wasn't there before, so it can't just be flowing from one to the other. What they noticed in both of those cases is that the amount of heat, or the creation of heat, was related to the motion of the objects involved. And so they got the clue that temperature, or heat, is really some sort of internal motion of the particles or the molecules that we can't see. This gives us our second two postulates of kinetic molecular theory. The particles that we can't see that make up material are always in motion, and they started to understand then that the temperature of those particles is related to the speed that they're traveling at, the average speed really. And looking at states of matter and things like that, they're able to come up with the idea that these particles must have some attractive forces between them. To talk about that in states of matter more, I will start another video.